Okay, now let's let A be 14, 9, the vector that we obtained previously, and let's calculate its length and its direction. Now, its length is just going to be how long it is, how far it is from this point to this point. Now, we don't have to know the initial or the terminal point. We simply know that if we go in the x direction, we have to go 14 units before turning at a right angle and going 9 units in the y direction. So this forms a right triangle with legs of 14 and 9. So the length of this vector and length is an instance of what we call magnitude, and magnitude is like an absolute value, but this isn't just a simple number. So we use kind of a double absolute value sign to indicate the magnitude of a vector. Some authors will use just a single absolute value sign. In any case, the length is an instance of magnitude A, and that's equal to the square root of the sum of the squares of its components because of the Pythagorean theorem. Okay, the length is certainly 14, square root of 14 squared plus 9 squared. And of course that's the square root of 277 if I do my arithmetic correctly. And that's approximately equal to 16.6. So we can say this is our vector A, and it has a magnitude that I'll label next to the vector of square root of 277, approximately equal to 16.6. So now we have the length of the vector, or the magnitude. In general, we talk about a magnitude because not all vectors are going to be displacement vectors, but we'll get to that shortly. Okay, so the magnitude of this vector is 16.6, approximately, more exactly 277. Again, check my arithmetic on that. Okay, what about the angle, or the direction? Well, direction is going to be specified by the angle with the positive x direction. And it's measured counterclockwise. So here's the positive x direction, so the angle is going to be measured counterclockwise from that direction. And we're going to call the angle theta. So using knowledge of trigonometry, and everybody should know the trigonometry, in this case the angle is theta, which is the arctangent of 9 over 14, and it's approximately 0.57 radians, and that's approximately 33 degrees. So now we can say that A is the vector of magnitude square root of 277 at approximate angle 0.57 radians, 37 degrees, or at exact angle arctangent of 9 over 14. So I write that as a statement. A is a vector of magnitude square root of 277, which is approximately 16.6. At angle theta equals arctangent of 9 over 14. This is exact, approximately 0.57 radians, approximately 33 degrees. Now, in general, the following rules follow in a very straightforward manner, and I'm assuming some background in trigonometry, so that this, and really anybody entering this course should already know all this. Okay, but a vector R has magnitude of R, angle theta. It also has components Rx and Ry. And as we've seen, we can specify the vector either by its magnitude and direction or by its components. And if we know the components, as we've seen here, we can easily calculate the magnitude and the direction. Now the rules are straightforward. The magnitude is calculated just using the Pythagorean theorem. And that should be very straightforward and obvious. The angle is calculated using the arctangent of the y component over the x, and this is because the tangent of this angle is the y component divided by the x component. Now, this angle isn't necessarily, the angle you get by taking the arctangent isn't necessarily the angle. We add 180 degrees or pi radians if the angle is less than 0. And typically we also, if we get a negative angle, we do the coterminal angle, whose angle is between 0 and 360 degrees, or between 0 and 2 pi radians. We'll see what that means here in just a minute. Okay, so these are the two rules. Okay, you can think about why this is the case. If Rx is less than 0, we've got to add 180 degrees or pi radians. It's simply because the arctangent gives us an angle between negative 90 degrees and positive 90 degrees. It's not going to give us an angle out here or down around here. And the reason, again, it's very easy to see if you think about it a little bit. The other set of rules are for calculating the x and y components if you know the magnitude and the angle. And those rules are very straightforward. The x component is the magnitude times the cosine of the angle. The y component is the magnitude times the sine of the angle. As you can clearly see just from this triangle, if this is the angle, then if I multiply the magnitude by the sine, I get this side. If I multiply the magnitude by the cosine, I get this side. And of course that needs to be second nature. We can't be stumbling over that and actually use vectors to do much of anything. So make sure we understand all that. Okay, now returning to our vectors A, B, and C, and I've color-coded B and C just so we can keep track of some of the labeling. Remember, A is the vector whose magnitude is the square root of 277, which is approximately 16.6, at an angle that's equal to the arctangent of 9 over 14, but that's approximately 33 degrees. And I didn't write down the arctangent of 9 over 14 simply because there isn't a lot of room here. Okay. Now, what about angle B and angle C? You should go ahead and calculate the magnitudes and angles of angles B and of vectors B and C. For the angles, for the magnitudes, I believe you get the square root of 392, and that's approximately 17.1. And it's not 392, it's 292. Because remember that B have components 6 and 16. 16 squared is 256, 6 squared is 36, and when we add those we get 292, not 392. I'll correct that next time I pause, which will be in just a minute, just a few seconds. And C, the components are 20 and negative 7. If I square 20, I get 400. If I square 7, I get 49. That's a total of 449. And when I take that square root, square root of 444 is 21. That comes out 21.2. Okay, now what about the angles? Okay, follow the rules carefully for the angles and see what you get. Okay, now if you follow the rules, plug in the Ry and the Rx here, you would have gotten negative 69 degrees, approximately. I think it would have been like negative 69 and a half or something like that. Okay, you would have gotten this. That's a negative angle, and you could certainly measure the angle down this way, because remember the angle is measured in the counterclockwise direction, so an angle that is measured down here is clockwise. That would correspond to a negative angle. So we could do negative 69 degrees here. I'm going to write that in lightly. Make this a little darker to make sure you can see it. But that's not the angle we really want to use. We want to keep our angles between 0 and 360 degrees. So, well, it's obvious that if we go 360 degrees, we go all the way around here, and then come back 69 degrees, we're going to have this angle here. And that's 360 degrees minus 69 degrees, 360 minus 69, and that's our 291 degrees, and that's the angle we're going to use because we want to keep our angles between 0 and 360. Makes it easier to keep track of quadrants and a lot of other things that will become apparent as we go through the course. Okay, if you do the same thing with this angle down here, I think you end up with an angle that we could measure from the positive x direction to be 341 degrees. Now I'll note again that all these angles are in either the first quadrant as the first one or in the fourth quadrant as these two. If an angle is in the the second or third quadrant, then the arctangent is not going to distinguish that. You have to make the judgment. If the x component had been 0 for any of these vectors, then we would have had to add 180 degrees. Anyone remember that? Now, we were originally given the components. Well, we were given 3 points and we found the components of these vectors. What we're going to do, though, is we're going to use the given approximations here, and we're going to calculate the x and y components of A based on our approximations, and the x and y components of B, again, based on our approximations. And then we're going to use those to approximate A plus B. We should get components that closely match those of our original C vector, and then we're going to determine the magnitude and angle of that vector. Now, there isn't a lot of space here, but the calculations are very straightforward. So for a vector R, we calculate Rx by multiplying its magnitude by the cosine of theta, the y component by multiplying the magnitude times the sine of theta. So we're going to put x component here, y component here for the vector A, and then same for the vector B, x component here, y component here, and then we're going to figure the sum A plus B, x component here, y component here. So you should do that. Take your calculator, run these calculations based on just the information we have here, not on the original components. Okay, A has magnitude that I'm going to use as 16.6, and I'm going to multiply that by the sine and cosine of 33 degrees. I'll get these results. Now this is close to the 14 and the 9 that we got before, but notice there's a tenth of a unit difference here. So we're not going to get exact results because we have round-offs in determining these angles and approximations in determining the magnitudes. Okay, for B, using magnitude 17.1 and angle 291 degrees, we get 6.1 and negative 16. Now that corresponds pretty well with the 6, negative 16 that we got, but notice we're off by a 0.1 here. And the 0.1 that we're here is low, the 0.1 here is high, so they're going to kind of balance out and give us the same result we got before, but we can't rely on that always happening when we do all this round off. So in this case, the little uncertainties balance out, and they often will, but they won't always do so. Kind of a 50-50 proposition. So C, the sum of A and B, has components, these components. That leads to C, magnitude 449, theta approximately 341 degrees, which agrees with what we had here. So that using just the angle and magnitude of each of these vectors, translating those into components, adding the components, and translating that back into an angle and a magnitude, we get the same thing that we expect to have gotten. Again, we expect to get close. We don't always expect it to come out exact because of the approximations involved. Observe very briefly that we can't just add the magnitudes to get the magnitude. We can't just add the angles to get the angles, but people are often tempted to do so.